So I'm going to go through some example projectile problems, showing how to set them up, how to solve them, kind of a little bit about the extra steps that need to be done compared to the one-dimensional motion, and also just kind of throwing out some more projectile motion understanding as we go through this. So I've already set the problem up. I've got the question, I've got it set up with the three S's, and I even threw some motion graphs down in the bottom corner just so that I can review those real quick as we go. But let's start the problem. We have a cannon that is um, F-worded horizontally. The F word is F-I-R-E-D. I'm sorry for spelling it, but there's some words that I just don't think are appropriate for a classroom. And this is one of them. So a cannon is F'd horizontally at 30 meters per second from the top of a 20-meter cliff. How far does the cannonball fly before hitting the ground, and how fast is it moving? So first step is we need to draw a sketch. And I'm just going to, it doesn't have to be good. I've just got my cannon. I've A'd it uh, in this direction. And I also don't say the A word, but it's going to F the cannonball along a path that looks, something like that. Initial velocity is going to be 30 meters per second, and it's starting from 20 meters up. So that's some of the information. Other things that we want to remember. One of our really big and important rules that we have in words in projectile motion is that we always have an acceleration down towards the ground. So I'm going to right now just put that in my sketch, and I want you to always do that as well. Anytime that you draw projectile motion, anytime that you know an object's in free fall like this one is, right away just draw in that acceleration downwards so you remember that it exists. The other thing that I want to put in here, that we always need to put in here, is a coordinate system. So I'm going to add a coordinate system. I'll do it in purple. Actually, I'll do it in blue. Actually, I'll do it in black. My goodness, Mr. Terrell, make up your mind. I'm going to have two coordinate systems. I'm going to have a horizontal coordinate system. So that's along the horizontal direction. I'm going to say to the right is positive. And in the vertical direction, I'm going to have down be my positive. But 0 is right here where the cannonball is exiting, right where it's SH'd from. Yeah, now that I've got all that set up, I should be able to go through my variables. And you can see that I set up two sets of variables. You have to have equations and variables for every dimension that exists. And since we have a position along the horizontal or a horizontal stuff going on and vertical, I have my horizontal variables and my vertical variables. I'll talk about time in a second. So going down the list, initial position according to my coordinate system is 0 meters. Final position, I guess I should draw that in because that's really the question here. That's x. So that's our unknown. This is what we need to know. This is the big question. Our initial velocity is given to us. Since it's going horizontally, we know that all of the velocity is in the x direction. So that's 30 meters per second. And then the final velocity will also be 30 meters per second. Remember that the horizontal velocity is always constant in a projectile problem, as long as we're assuming the air resistance is negligible, which is a safe assumption to make in this case. Or I should have just said air resistance was negligible in the question. So it says that now. And then finally, the horizontal acceleration, AX, is 0, because like I said, as long as air resistance isn't a factor, which we're going to assume most of the time it is not, the horizontal acceleration is 0. Now for the y variables, because I set my initial position there, my initial height is 0. My final height will be 20 meters, because this is my positive direction and the ground is 20 meters away. My initial velocity is 0 because, like I said, it's being F'd horizontally, which means none of this 30 meters per second is vertical. There will be vertical velocity in moments after it's F'd, but at the moment, the initial moment, V naught, it's still 0. My final velocity, we don't know that, and that's part of the question. That's this. How fast is it moving? So we'll solve for that. And then finally, we have vertical acceleration. And I'm going to write in g. Even though we know that's 10 meters per second, I want you guys to get in the habit of thinking of acceleration as g instead of as a number. So I'm going to write it in as g, and later we'll substitute in 10 when we need to. But I'm going to put in g there, and g is going to appear in all my equations until the very end. And it's positive g because I said down was positive, and the direction of my g right here is down, which means it's in my positive direction. Finally, time we don't know yet, but time is our unifying variable between the two. I said in the last set of videos that in a lot of your projectile problems, what you're going to need to do is you're going to solve for the time of flight using the y equations. We're going to find out how long it takes for this ball to just fall and hit the ground. And then once I know that time, I can plug that time into my x equations and figure out how far over it got. So that's why it's purple here, is because it's the shared variable between the two. At any time that it's in the y, there's also, I can plug that same time into the x to get its exact coordinates in space. So now it's time to solve. And like I said, I'm going to start with the y variables. So I'm going to use this equation, the second kinematic equation. And the rationale for using this equation is because if we're doing kinematics or projectile problems, a lot of the time we know position information and we want to find out how long it takes to hit the ground. But since hitting the ground is a height issue, and how long is a time issue, we need this equation to figure it out. So I have this set of variables here. My initial velocity is 0, so I can get rid of that whole v naught y term. My initial position is 0, so I can get rid of that whole term. And it simplifies to y equals 1/2 at squared. And I'm actually going to turn that a into a g because the acceleration is g. And now I just need to solve for time. So the best way to solve for time, if I multiply both sides by 2, that'll cancel the half. If I divide both sides by g, that'll cancel the g's. And if I square root both sides, that'll get rid of the square roots. And I know that was ugly. It cleans up to look like this. T equals the square root of 2 times y over g. And I'm just going to write that in right now. I'm not even going to bother evaluating that expression. I'm going to put it in here. And I want you, again, to be in that habit of leaving things in variable form for as long as possible. One reason is because sometimes surprising variables cancel out. And by doing this way, you'll start getting a sense for like what you need and what you don't need. The other reason is I want you guys to get comfortable dealing with variables instead of numbers. So let's leave it in variable form for as long as possible. All right, so now that I have that, I'm going to set up the x equation. Again, I'm trying to figure out how far it goes over in this time that it was given. So I need the second kinematic equation in order to set that up. Now, from my list of x variables, my initial position is 0. I have 0 acceleration, so I can get rid of 2 of my terms, and I just get x equals v naught times t. So v naught we already know. That's v naught. And then we have the time from right here. I'm going to write it in purple just because, I don't know, maybe I should write it in red, but whatever. 2y over g. So now that I know that, I'll do the rest in purple. Now that I know that, I can actually, no, I'm going to do it in black. In black, I can solve the rest of it. The initial velocity is 30. 2, my y is 20. This is all over g, which is, I guess, 10. So that's 2 times 20 divided by 10. Conveniently, it works out to be 4. I kind of did that on purpose, so my math would be easy. So the square root of 4 is 2. So this ends up traveling 60 meters, which actually isn't that impressive for a cannonball, is it? 60 meters? No, that's not really that impressive. Probably a cannon gets effed a lot faster than that, but there's our answer. We now know that it's 60 meters. So that's how we solve that. I'm going to go through the position and time graphs real quickly. So for the position graph, we know that the velocity in the x direction is constant. So it has this nice flat line, which means the acceleration is 0. But the implication of this, if we have a constant velocity, is that the x is going to increase constantly. up until we get to the time that we hit the ground, and then it stops or it has a different acceleration as it rolls or bounces or whatever. But we cared about this time, so this is where we got to t, and this is where we got to, 60 meters. That was 30, this was 0. Now for the horizontal direction, or the vertical direction, I'm sorry. In the vertical direction, we had a positive acceleration because I said downwards was positive. We started with 0 initial velocity, but then the vertical velocity just increased because we had a positive acceleration. So since the acceleration was constant, we have a linear graph for the velocity. And then the y graph is, it needs to get steeper over time. So we're starting from 0 because that's our coordinate system, but then it's just going to get steeper and steeper and steeper and steeper and steeper as it falls until it gets to right here at also at t, but that t is at 20 meters in the vertical direction because that's how high or how far it fell. So there's our first practice problem. I hope this sets you guys up to be successful on understanding these kind of problems. Cool, bye.